All right, everybody, welcome back to another chapter. So today we're going to go ahead and start kind of a fundamental shift in the ideas that we're talking about in this class, in the context that the past several chapters have really been about background ideas, but now we're going to start focusing on specific objects, specific things, specific groups within the actual universe itself. And chapter 7 is just a nice introduction to that, by starting off with our local solar system, some of the bigger ideas, not necessarily all of the ideas, but some of the bigger ideas that we have about our solar system. And this picture that you see right here, this gives us kind of an artist depiction of what the organization of most of our solar system looks like. We have planets, sometimes kind of classified in a very specific way, as we're about to find out, that are close to the sun. There's this interesting division between the next group of planets that are a little bit further away. And then there's this kind of nice firm boundary out near the kind of far right-hand side that we'll talk about as well in a future chapter. So let's go ahead and kind of look at the fundamental kind of objects in our solar system in an introductory kind of sense. So what we'll say is that when it comes to our solar system, the two dominant objects in our solar system are stars and planets. Now, to be particular, we only have one star, the sun. As we'll find out in future chapters, that's actually abnormal, but still, we have one star, and we have 8 planets. Now, in a future chapter, we'll talk about why we used to have 9, but currently have 8 planets. It's a very interesting story. But nonetheless, for this slide right here, we just want to focus on some differences and, to some extent, similarities between these two dominant objects in our solar system. So one of the things that we said in chapter 5 is that when it comes to a black body object, like a star, like the sun, for example, they are unique in the sense that they will absorb and they will emit, most importantly, every color of light, ideally in equal amounts, but again, according to the black body curves that we saw, those light curves, there was always a peak wavelength, a dominant color. But nonetheless, they emitted every color of light possible to be classified as a black body, or to a lesser extent, a pseudo black body. And the key thing about a planet, though, is that in comparison, planets, they do absorb some light. That's how, for example, the Earth's surface gets warm, and you can kind of feel that when you touch, for example, pavement during the daytime. It's very, very hot, the blacktop, for example. But it also turns out that the planets like Earth, they also reflect light. So, for example, ice is actually quite shiny, quite reflective, and so therefore this kind of polar ice caps of the Earth reflect back a lot of light that is incident on them, as we'll talk about again in a future chapter very shortly. And lastly, it turns out that planets, even though they are not black bodies, they do emit light because they do have a temperature that's above 0 Kelvin, just like we talked about in chapter 5. So planets are unique in the sense that they absorb light, they do emit some light, but they also reflect a fair amount of light as well. And you can see that represented here in the picture on the right-hand side. And the key thing about this kind of picture that's on the right-hand side is you can see in yellow the incident or the incoming light from the sun, this kind of part of the picture right here. We can see some of that light being reflected off of the surface, kind of these wavy yellow lines coming off right here. Here they kind of talk about how light can be absorbed by the surface to get it warmer, to heat it up. And then here in the red, this constitutes the light being emitted by a planet, predominantly infrared light, but there could be other wavelengths as well. But this is kind of the key difference between planets and stars. And that's something that we're going to kind of definitely talk more about in future chapters. But we need to have that kind of fact starting off our discussion in chapter 7. Because now what we're going to go ahead and do is we're going to start talking about some of the characteristics of the planets within our solar system. And it turns out that of the 8 planets that we have in our solar system, they can be divided into 2 classifications, 2 categories. And what we can say is that the first classification of planets are what we're going to call the terrestrial planets, sometimes called the inner planets because they are closest to the sun. So those planets in increasing order distance from the sun, you have Mercury, Venus, Earth, and Mars. And you can see in this picture here on the bottom what each of these planets look like. Now, as a slight disclaimer, some of the pictures below are a little bit deceptive, and we'll talk about why in future chapters. But these are pictures of the innermost planets in that order. Now, what makes these planets all have kind of a commonality to be classified in this way? Well, it turns out that the characteristics that they all share is, first off, their small size. And small, again, is a qualitative label. It is subjective. What we really mean to say is that they are small in comparison to the other category of planets. But nonetheless, they are small in radius, they're small in diameter, they're small in size. They have rocky surfaces, and they have thin atmospheres. And again, thin is subjective, but thin compared to the other category of planets. Because as it turns out that one of the planets, I don't want to ruin the surprise, has an atmosphere that is insanely thick compared to our own atmosphere, which is thick compared to 2 other planets within this group of 4 that we have right here. But these planets are unique in the sense that they're all close to the sun, and they all share this interesting kind of commonality in regards to their atmospheres, their surface composition, and their interior composition to the best of our knowledge. And also, interestingly enough, their small size, as we'll find out later, due to their composition. Now, the second category of planets that we have in our solar system, they are called the Jovian planets. Now, a lot of students by accident will put an L at the end and call them the jovial planets. Well, jovial means happy, and these are planets. They don't have emotions, so that's kind of a silly thing to do, but it is surprisingly and depressingly common. But sometimes these are called the outermost planets because they are admittedly the furthest planets away from the sun. And again, here is a picture on the left of what these planets look like. And these pictures are pretty straightforward. There's no kind of special disclaimer that I need to say about them, other than the fact that they're fairly old pictures. Most of these pictures you see here were probably taken from the 70s or the 80s. So that's a long time ago, but still good enough quality for us to look at them in the first part of chapter 7. So these planets, Jupiter, Saturn, Uranus, and Neptune, and that is something I do want to mention. The joke, in astronomy is Uranus. Well, it's not a hard A sound. You don't go anus because it kind of looks and sounds funny. It's just soft A sound, so Uranus. Now these Jovian planets, they have a large size in comparison to the terrestrial planets. Their composition is that they are filled primarily with gases, liquids, slushy ices, kind of like if you were to go to a 7-Eleven and get kind of a slush, or if you were to go to Sonic and get a slush there, although that's not quite the same, but slushy ices. So that's the consistency that we're going to be kind of thinking about in this case. And the other thing that's important about these outer planets is that they don't have a solid surface, the way that the inner planets do have a solid surface. So for example, on Earth, there is a surface, okay, because we're sitting on it basically. But for example, on Mars, there is a surface to land a rover, to land a spacecraft onto that surface to study it. But there's no such thing that can be done for Jupiter, for example. Jupiter has an atmosphere, and then its composition changes to that of, again, kind of a gaseous, liquid, slushy ice kind of texture that we'll talk much more about in detail in a couple of chapters. So it seems kind of weird for a planet to not have a solid surface, but that's actually surprisingly common, as we'll talk about in future chapters with other planets, these foreign planets, exoplanets, when we get there in that chapter. Now, the other thing that is worth mentioning, though, is that even though these outer planets don't have a solid surface to land a spacecraft upon or to touch down upon, they do have a theoretical solid core at their center. And that's going to tie into this idea of the formation of our solar system a little bit later on down the road. But the key idea is that it is a theoretical idea. The mathematics makes sense that it should be there, but we haven't really been able to test whether or not it does have a solid core, because the spacecraft that we can send to these planets tend to get destroyed pretty early on into the entry of the atmosphere of these planets. So our data is limited, but based upon the math and the physics, they should have a solid core in their center. All right, well, our solar system isn't only planets and stars, there are other members. So for example, this idea of Pluto, not shown in the picture on the left, and Ceres, also not shown on the picture on the left, but it was kind of mentioned, or it was kind of shown in the very first picture in the chapter. So if you forgot what that looked like, rewind the video and then come back when you're ready. But these objects are called dwarf planets, and we're going to talk more about what a dwarf planet is when we start talking about the outer planets in that chapter. I believe it's chapter 11 when we get there. So I'll go ahead and kind of wait on defining what they are. I'm just going to introduce the fact that they exist within our solar system. And there are many dwarf planets that exist. Pluto is the most famous one, but Ceres, at least in the astronomy community, is equally important just because of how odd it is, and especially where it's located within our solar system. Now, the next kind of noteworthy group or other member within our solar system are asteroids. And again, this kind of gets its own separate chapter, in effect, later on in this kind of semester. But there are two kind of well-known asteroids in the picture that's on your left. Gaspra, which is basically this little guy here in the middle, and then Eros directly above it. Now, admittedly, Matilda and Ida and Dactyl and Temple 1, they are all definitely asteroids as well. And even Itokawa, down here on the bottom left, is also an asteroid. And the one thing that I want you to notice here, something that we're going to dwell upon more in a future chapter, is that asteroids, they tend to span the range of sizes, but they tend to be relatively small compared to a planet, for example, even a dwarf planet like Pluto in this case. Now, I didn't mention Phobos and Deimos, and that's because they are actually moons of a planet. I don't want to, again, spoil the surprise, but the consensus in modern astronomy, circa 2020, is we think that Phobos and Deimos were at one time in their distant past asteroids, but then they got too close to the planet that we'll find out that they belong to now, and therefore have now become moons, or sometimes we call them satellites, of the planet in question. So that's why they're kind of lumped in this picture, because at one time they were definitely asteroids, but along the way they changed their association to become moons of planets. Now, it turns out that comets are easily confused with asteroids, but again, comets, they're kind of not part of their own chapter, but they are a separate chapter from asteroids. And we're going to find out that they do have a lot of differences between them. The two most well-known comets, not shown in the picture on the left, are Halley's Comet and then Hale-Bopp, which is lesser known, but to the older generation, my generation and older, we remember Hale-Bopp. It had a very interesting backstory that I'll talk about in that future chapter. But it turns out that Wild 2 here on the bottom left is in fact a comet as well. You'll notice that it's very, very bright in comparison to the other objects in the pictures that are much darker in comparison. That's one of the giveaways that it's probably a comet and not an asteroid. It's not a guarantee, but it's compelling evidence, put it that way. And then again, I kind of hinted at this already, but there are many moons within our solar system. Turns out the outer planets have more moons than the inner planets by far. It's kind of laughable in that case. But just to name a few of them, we have Phobos kind of in the top left of this picture, we have Io, we have our moon, and we have dozens and dozens and dozens and dozens and dozens upon dozens of moons that also exist within our solar system. We're going to talk about some of the more noteworthy moons in chapter 12, I believe, but I could be mistaken in the current edition of our textbook. but we will get to them later on. All right, well, since we've now kind of introduced the broad, general kind of groups, objects within our solar system, now let's go ahead and focus more specifically on behaviors that are kind of relative, or kind of behaviors that are specific to planets like the Earth, for example. And one of the more kind of cute sayings that is known kind of in everyday conversation about the Earth is that usually the Earth is colloquially referred to as the third rock from the sun. You know, it's a cute saying, and there is some truth in the statement. But it turns out that the Earth, it's more than just a rock, the third one from the sun. It turns out that the Earth's crust, in terms of its composition, is surprisingly complex, more than you might have thought. And this pie chart right here gives you kind of a percentage representation, not a raw material amount, but a percentage representation of what the Earth's crust consists of. And the one thing that I want you to kind of notice about, which might be a little surprising, is that almost half of the Earth's crust is oxygen. Now that's going to be weird, because when you think of oxygen, most likely what you're thinking about is like air, for example. All right. Well, don't forget that oxygen is just an atom. That's all that these kind of labels are. Oxygen, silicon, magnesium, potassium, aluminum. These are just atoms. These are just elements within the periodic table. So for example, think about water. Water is dihydrogen monoxide, aka H2O. So the oxygen that's in water is something that you might not think about, because oxygen is gas in your daily experience, but water is liquid in your daily experience. Turns out the same thing is true for the materials that are on the Earth's crust. It turns out that a lot of the rocks within the Earth's crust have an oxygen content to them. And because of that, there's a large amount of oxygen in solid form, not necessarily in gaseous or even liquid form, but there's a lot of oxygen in solid form within the rocks of our crust. Surprising, but true. The next dominant element that's in our Earth's crust is silicon, and that might not be kind of familiar to you. And no, it's not silicone, don't add an E to the end, but silicon. It turns out that that is the primary ingredient in what we have a large amount of in California. Well, what do I mean by that? Well, turns out sand. It turns out that the biggest ingredient, the biggest element in sand is silicon. In all the computer chips that are in your smartphones and tablets and things like that, silicon as well. So there's a large amount of silicon element. There's a large number of silicon atoms within the crust of our planet. And all the other ones that have smaller percentages, aluminum, iron, calcium, you don't need to memorize the percentages, that's okay. Just kind of be aware that oxygen, weirdly enough, is the dominant element within the crust of our planet. And furthermore, you'll notice that on the right-hand side, there is a kind of labeling by aluminum, iron, calcium being classified as metals. And then even furthermore, calcium, sodium, potassium are further subdivided into what are called bases. This is more of a chemistry label, so we're not going to care too much about that in this class, just a very soft mention and that's it. And same thing with metals. We will use that term on again, off again throughout the semester. And basically, metals are just a very specific type of solid that kind of interact chemically in very interesting ways, and hence they're labeled as metals as a consequence. We're not too concerned about the definition. Just kind of be aware that aluminum, iron, calcium, sodium, potassium, magnesium, and others can be classified as kind of metals in this case. All right, well, it's interesting that we have this information in the pie chart, but the underlying question that we should be asking is, how do we know that there's roughly 47% oxygen in the crust? How do we know that there's 28% silicon, roughly speaking, in the crust? So how do we know this information? And it turns out the way that we figure that out, it's quite complex, but in Astronomy 20, we're going to learn about the more basic technique that could be used. to get a very rough idea, a very rough understanding of the composition of a planet's crust. Not as detailed as this, but kind of a surface level, cute phrase on my part, but a surface level understanding of this idea of determining composition. We use this process in science called ballparking, or in physics, it's more formally called estimation. And the way that that works is that if we wanted to determine the density of the Earth, and again, back from previous chapters when we talked about the difference between mass, density, and weight, we said that density just kind of corresponds to the composition, numerically speaking, but it's the composition of a material, since each material in the periodic table, each atom, each element, better said, has a unique density compared to every other element within that periodic table. So the way that we approximate the density of the Earth, or really any object for in this case, is by comparing or kind of dividing two numbers to each other. The first of those two numbers is the mass of the object in question, Earth in this case. The denominator, represented by capital V, represents the volume, aka how much space the Earth takes up in this case. And it turns out that the volume of the Earth has been known for quite a long time. In fact, if you go back to chapter 2, for example, we determined that Eratosthenes, he was able to figure out the circumference of the Earth to a high degree of accuracy long ago during the ancient Greek Empire. And it turns out from geometry, if you know the circumference of a circle, then you can figure out the volume of the sphere that the circle is a part of, kind of like a slice of the circle. So, sorry, a slice of the sphere, so to speak. But the volume of the Earth has been known for quite some time. It's the numerator, or the mass, that has been particularly tricky to figure out. It turns out that the mass of the Earth, it really wasn't figured out accurately until the 1800s in physics. Prior to that, the mass of the Earth was really estimated, and the estimations, as it turns out, were quite horrendous. But starting in the 1800s, we got decent accuracy to the Earth's mass, and therefore we were able to get decent calculations of the density of the Earth. But the one thing I do want to mention, though, is that because this fraction is so simple in that it's total mass divided by total volume, then what we get back is an average density. And this is important because average density doesn't give you specific, detailed composition information. Average density is just that. It's an average value. So for example, if you think about your body is made up of flesh and blood and muscle and bone and sinew and tissue and things of that nature. And you could figure out the density of your total body on average, including all these unique pieces that go into it. But that number that would come out of there wouldn't give you a specific representation for what's on your left side on the top part of your body, or the right side on the bottom part of your body, aka that density that would be for your entire body wouldn't be the same density as just your toenails, or the same density as just your hair follicles. It would be an average, or kind of a combined value that takes everything and just kind of blurs it together into a single number. So we lose information in this process, but at least we get some level of insight in terms of the composition. And what's important is that for the Earth, its average composition, its average density, turns out to be a value which is coming from your textbook of 5.514 grams per cubic centimeter. And this is one of those numbers that I recommend you put onto your note card, because this is a number that you're not going to have to do calculations with, but it's going to be a reference for answering questions or understanding behaviors in this chapter and in future chapters as well. What do I mean by that? Well, for example, if you have one number by itself, it doesn't really tell you a lot. So for example, if I tell you the number 55, okay, well, it's just one number. It doesn't mean anything. But if I said that I have $55 and you have $35, okay, now that we have two numbers, we can do a comparison to understand my wealth in dollars to your wealth in dollars. The same thing is true for density. One number by itself, kind of boring, can't do much with it. But two numbers, and we can do a comparison to understand which one is more or greater or lesser than the other one in comparison. And it turns out that from geology, we know that something called basalt rock, which is kind of like lava rock that you see right here in the rightmost picture, it turns out that basalt rock has a density on average of about 3.3 grams per cubic centimeter. And what's important to kind of recognize about this comparison is that the Earth as a whole, the Earth on average, has a density that's almost twice as much as that of stereotypical rock, aka basalt rock. So the conclusion that we can draw just based on this very rough idea is that the Earth has more heavy materials, higher density materials than just rock, because its average density is more than just rock as well. So by looking at the density of a planet, for example, or just an object in our solar system, we can get a rough idea of its composition. If its density is very high above that of basalt rock, it's probably going to have a lot of metal in its interior. If its density is below basalt rock, then it's probably going to have more liquids and less solids in its interior. So we can't tell specific information about the object in question, but we can get a rough idea about its composition, metal-wise or liquid-wise, because it turns out that liquids like water have a lower density than something like aluminum. A good example of why that works is, for example, think about the last time you went to a mall, like for example, the Irvine Spectrum Center or something like that. Usually at malls, there are water fountains. And here in the United States, what do you do for good luck at a water fountain? Well, you don't jump in because it's just dirty water, but you throw a coin into the water fountain. And when you throw a coin into the water fountain, what happens to it? It sinks to the bottom. A leaf, on the other hand, when it falls into the water fountain, it doesn't really sink to the bottom. They tend to float in comparison. So that's kind of where this next idea comes into play as well. Because if we know that a planet like Earth has a very, very, very high density compared to basalt rock, then we know that there's going to be a large amount of metal in its entirety. Not so much just its surface, but in its entirety. But it turns out that just like throwing the coin into water, because the coin, which is made of something like aluminum or copper or something like that, due to its higher density, it's going to want to sink to the bottom of that container. And the same thing actually happened with Earth. We're going to talk more about those details in chapter 8. But it turns out that long ago in the Earth's past, the metal that made up the Earth, it kind of, for the most part, and there's always exceptions because we know there's metal in the crust, but a large amount of the metal within the Earth sunk down to its center. And the lighter materials, the silicon, for example, it tended to kind of float to the top, kind of like a leaf would do in that fountain example that I gave you from before. And that separation, that differentiation, as we call it, it gave the Earth's interior, or the kind of planet in question, like for example, Mars, Venus, or Mercury, it gave it a very unique, separated, or differentiated structure. And we'll talk more about this in chapter 8 when we get there, but the high density metal formed the core of a planet like the Earth, and the lithosphere, or the crust, as we call it in Astronomy 20, is made primarily of the actual kind of silicate material, the lighter, lower density material that made up the Earth long ago in its past when things could float or sink more easily. Nowadays, the Earth has actually cooled off, and you might not feel that way, but the Earth has cooled off dramatically in the very long period of time that it has been not alive, but the time that it has existed in our solar system. And because of that cooling off behavior, this migration of material, this differentiation process has effectively stopped. It's occurring in extremely small scales now, but the actual kind of big picture of it has stopped because of the Earth cooling down over the course of several billion years, turns out. So this picture right here gives you kind of an artist's representation of the differentiation within a planet like Earth. And it turns out that the outer planets are also differentiated, not so much in a kind of hot way that we have with the Earth, but in a way that kind of deals with liquids and solids, kind of the slushy ices, the liquids and the gases that we talked about in the previous part of this chapter. So the outer planets are differentiated, but theirs is a little bit more complicated. But the Earth, if you were to kind of look at its kind of layers, kind of like the nesting dolls that you kind of see from Russia, for example, kind of the tourist things that you can get from Russia, the nested dolls. If you look at the structure of the Earth, here we have the hottest part of the Earth, its core, made of primarily of nickel and iron, two very kind of high dense metals. There's other metals in there, but overwhelmingly, laughably, nickel and iron. The outer layers, they're made up of more kind of dense rocky materials. And then at the very kind of outermost edge, kind of like the skin of the apple, or kind of just like the crust of our planet in this case, we have lower density rocky materials, aka kind of your basalt rock and things of that nature. But this degree of organization within a planet itself is itself noteworthy. It's not just kind of a random spreading out of materials like you might expect. The Earth is highly ordered in its concentration, but it's primarily due to density. High density will sink to the bottom, and lower density will kind of float to the top in this case. Always exceptions. For example, think about a battleship. What are battleships made of, material-wise? Metal. If I take a piece of metal and just throw it into the ocean, what's going to happen? It's going to sink. Well, what is inside a battleship? Air, breathable air. And it turns out the density of air is really low compared to the density of water. So the density of the metal and the air, on average, is low enough to make a battleship float and not just flat out sink, killing everyone inside. So this idea of determining composition by using density, it also gives us a little bit of insight into this idea of the differentiation, the kind of separation by material within the planet itself as well. But one of the kind of last aspects in chapter 7 that we're going to focus on here is this idea of trying to determine how old a planet or how old an object is within our solar system. And it turns out the first serious attempt to determine the age of a planet, for example, or a moon or something solid like that, was to use geology, in the sense that if we were able to count the number of craters, impacts from foreign sources that are visible within a certain size, a certain area of the planet in question or the object in question, we could use that counting, we can use that number and compare it to the Earth to determine, roughly speaking, how old the object is in comparison to the Earth. You could argue that it's kind of like comparing the wrinkles in skin. Younger people tend to have fewer wrinkles. Older people tend to have more wrinkles in their skin. So by counting the number of wrinkles in your forehead, I can get a rough estimate of how old you are compared to a 70-year-old person who has lots of wrinkles in comparison. It's not the greatest technique that was available, but it was one of the earlier techniques that was available to astronomers and geologists, because they tended to work hand in hand in this endeavor, to try to determine the age of objects in our solar system. So it wasn't very precise, but it was a reliable method. So in this picture that you see right here, those yellow dots represent impact craters. The red dots, interestingly enough, correspond to locations where astronauts landed on the moon, and we'll talk more about that in chapter, I think it's going to be chapter 9 when we get there. But you'll notice here that some of these little grids and these black lines have been added in artificially by scientists. That way we can subdivide the moon here into various quadrants, into various sections. And you'll notice that some sections have more impact craters than others, like this has just one, whereas this has, 2, 4, 6 in comparison. But if I can find the number of impact craters, I can get an average for all these sections, and therefore I can get an average number for the entire planet, the entire moon, the entire object in question, and then compare that to Earth. The more craters that an object has, the older that it is. The fewer craters that it has, the younger it is. And again, that corresponds to kind of like wrinkles in people's skin. If you're old, you're going to have more wrinkles. If you're young, you're probably going to have fewer wrinkles. There's always exceptions, but for the most part, that's the behavior of the group, basically. Now, that method, like I said, it's not very accurate. It's not very precise for reasons that we'll talk about in chapter 9 and 10 when we get there. But it turns out that starting in the 1970s, the very late 70s, there was an alternative way that we could use to much more accurately determine the age of an object in the solar system. But the technology wasn't available. Technically, the data wasn't available until the 1970s. And why the 1970s? Why not the 60s, the 50s, the 40s, or before that? Well, it turns out that in the 1960s, late 1969, it turns out that something incredible happened in terms of human achievement. Human beings set foot on an object other than the Earth, aka the moon landing with Neil Armstrong, Buzz Aldrin. What's important about that is they brought back with them rocks from the moon. And that means that geological experiments could be done on moon rocks. And interestingly enough, those rocks helped us determine the age of the moon compared to the age of the Earth. But getting back to this kind of counting method here, turns out that if you look at this picture of Mars, each of those white circles corresponds to a verified impact crater. And what I want you to kind of notice is that if you look at this picture here and compare it to the one from before, compare that to the one from before, you'll notice that the moon has a lot of impact craters. So by that logic, the moon is quite old, and Mars has fewer impact craters. So you would say, okay, Mars is much younger in comparison. How much younger, we can't really say, but it would be younger in comparison. But it turns out that's not actually true. That method gives us a false result. So to understand the true result, the actual kind of method that's still used in modern day times, we have to understand this symbol that you see right here. And depending upon your background and life experience, you might recognize what this symbol means. It's not a biohazard symbol. That looks similar, but it is different. This is the symbol for radioactivity, radiation. Okay, most people have a very negative view of radioactivity. It's actually quite benign in physics. It's quite benign in astronomy. It turns out that there is a process in physics and astronomy as well called radioactive dating. It is a way to determine the date or the age of an object in question using the idea of radioactivity. Now, first off, the picture that's here on the right-hand side, you might have seen this before, especially maybe in your grandparents' kind of garage, or great-grandparents, if they're still alive, their garage. This is a Geiger counter. It allows scientists and just people in general to measure certain types of radiation. Now, the picture on your left kind of relates radioactivity to light back from chapter 5, in the sense that a light bulb or the sun, it has the ability to produce light, to emit light. So light bulbs produce radiation. We call it electromagnetic radiation, but they produce radiation, or they radiate, as we sometimes say. But a radioactive substance, for example, like uranium, it also produces radiation. It also emits radiation. It's not necessarily electromagnetic. It can be, which we'll talk a teensy bit about. But radioactive elements like uranium, plutonium, strontium, things of that nature, they emit radiation of some type, not necessarily electromagnetic, but they emit radiation in the same way that a light bulb emits electromagnetic radiation. And that's what that left picture is trying to tell us. And that's important because we were able to understand electromagnetic radiation from light sources like stars back in chapter 5 and a little bit in 6 as well. So if we were able to understand that behavior in chapter 5, then there's no reason why we can't understand a similar behavior for radioactive rocks, quote unquote, really metals, but rocks, we'll say, that are on the Earth's surface or within the Earth itself or coming from the moon, for example. So what are we able to do? How do we do this? Well, the first thing that we have to do is to understand and to be able to use radioactive dating. We have to be able to examine the elements within individual rocks. So does the rock contain only silicon? Does it contain silicon and oxygen? Does it contain silicon, oxygen, and potassium? What exactly is inside this rock? And that can be done with chemical testing, aka spray a chemical on the rock. If there's a chemical reaction, then you know there's a certain material, maybe, for example, silicon, in that rock. All right. So we need to figure out what's inside the rocks, and that can be easily done. And it turns out that there are many different sources of rocks. There are many different types of rocks that we have kind of looked at using this process. So for example, we have this idea of rocks from the Earth itself, its crust. We have rocks that were brought back from the moon, which we've also investigated. There are things that we talked about before, asteroids, that we were able to kind of get rock samples of, and we'll talk about how that could be done in a future chapter. And then also, again, in a similar future chapter, there's something called meteoroids. And those are basically rocks from space that have landed on Earth. There's more to it than that, but that's the kind of shrimp appetizer version of what a meteoroid is. But all four of these types of rocks, we can analyze their composition. And by knowing their composition, we can figure out their date or their age using this process that we're about to talk about right here. And it turns out that the process of radioactive dating, it relies upon this process in physics called nuclear fission. Okay, well, the first word nuclear is synonymous with nucleus, like nucleus of an atom, for example. The word fission is where things get interesting. So what we're going to say is that fission is a process in which one object splits into two or more pieces. But it happens, in the case of this chapter right here, spontaneously. It can be forced to happen, but that's a little bit more of a physics kind of thing. For astronomy, we care about spontaneous nuclear fission, where it just kind of occurs on its own. And what we're going to say is that radioactive elements like uranium, plutonium, things like that, they undergo spontaneous nuclear fission. And what's going to be kind of weird is that you'll notice that here on the bottom left, I'm showing a picture of bananas. And that seems kind of weird, but it turns out that inside bananas is the element potassium. Okay. And it turns out that potassium, it is needed for human bodies. If you don't get enough potassium, your bones are going to start to get brittle, and that's not good for you. It's just like calcium, turns out. So you need potassium, otherwise your bones are going to break and you're going to die. But it turns out that the potassium inside bananas is a little bit more than we expect. What do I mean by that? Well, most of the potassium inside bananas is benign. It's boring. But a small, and I can't emphasize that word enough, but a small percentage of the potassium within bananas is in fact radioactive. There are radioactive isotopes of potassium inside each banana that you eat. All right, now I need to pause right there because automatic, I can kind of feel a few of you guys pulling away. I am not anti-banana. I'm not part of the anti-banana conspiracy. I love bananas. I eat them from time to time. But it turns out that because of the way that bananas absorb nutrients from the Earth's soil, there is radioactive potassium all throughout the Earth's crust. There's not a lot of it, but it's ubiquitous. It's just everywhere. And when banana trees absorb those nutrients into their roots, they carry them into the fruit, aka the bananas themselves. And this is going to be important for us because it turns out that if you were to look at a single banana, the amount of radioactive potassium in a single banana is laughable. To be honest, if you wanted to get radiation poisoning by eating bananas, you would have to eat a ton of bananas every day for a year straight to get noticeable symptoms of radioactive poisoning. And your stomach just isn't big enough to eat a ton of bananas every day. So it is okay to keep eating bananas. Again, they taste great. I recommend that you do so anyways. But the fact that there's radioactive potassium in bananas is of interest to us because we can use that radioactivity, this fission of those atoms, to help figure out the age of the banana in question, for example. So what we're going to say, using specific terminology, is that when nuclear fission occurs, the parent nucleus decays into daughter nuclei. And that's a very kind of odd choice of words, but this is coming straight from physics. So for example, if you look at the radioactive decay of uranium, so again, back from chapter 3, when we talked about this, U is the abbreviation for uranium in the periodic table. 92 corresponds to the number of protons, in this case colored pink, that are within the nucleus of this atom. The electrons are not shown, we don't care about them. And this number 238, this is the nucleon number, or the total number of particles within the nucleus, protons plus neutrons added together. And what you'll notice here is that this one single nucleus, called the parent nucleus, it fissions, it decays, it splits into 2 daughter nuclei, something that's called thorium, which we don't care too much about in this class, and then something else, helium, interestingly enough, historically called an alpha particle in this case. But this occurs for every type of nuclear fission, not just uranium, but everything that is radioactive will at some point undergo spontaneous decay into 2 or more daughter nuclei. We're going to focus on the case of 2 daughter nuclei, but it could be more. It's possible. So for example, in moon rocks, in the rocks that we tend to study in astronomy, we tend to focus on determining the concentration, the amount of argon and potassium in these rock samples. And the reason why is that when radioactive potassium, similar to the potassium that's inside the bananas, that's radioactive, when that undergoes nuclear fission, those atoms, they have a certain probability of undergoing radioactive decay and turning into argon, aka argon is one of the 2 daughter nuclei. Now, there is a certain percentage that it could also turn into a calcium atom. So that's kind of what this other branch of the picture represents. And this is where physics gets quite complicated. But we're going to focus on the left transition from potassium K. I know, weird abbreviation, but look to the chemistry people. They chose them. But potassium can turn into argon, and it emits a gamma ray photon, weirdly enough, when that process occurs. It doesn't produce an alpha particle. That's unique to uranium and several other elements. But it turns out that potassium releases a gamma ray photon of light when it undergoes this fission event. So what happens? How is this helpful to us? Well, if we're able to figure out the concentration of argon and the concentration of potassium within a rock sample, that fraction, that ratio, can give us the age of that rock when it was formed in our solar system. How does that work? Well, again, this is a physics idea, but the way that it works is that we can look at this idea of what is called half-life. Now, that's not just a really cool video game that you might play, but half-life corresponds to a very specific amount of time that a radioactive sample is required to undergo in order for half of that sample to have spontaneously decayed into its daughter nuclei. And it turns out that half-life, it is element specific. So for example, the half-life of uranium is noticeably different than the half-life of plutonium, or the half-life of potassium, or the half-life of strontium, or the half-life of any other element that's radioactive in the periodic table. So why is this kind of helpful to us? Well, it turns out that mathematically, the number of parent atoms, potassium in our case, it decreases over time due to the spontaneous fission occurring within these atoms. So that blue curve represents the number of parent nuclei. And you'll notice that in the beginning, we start off with the number 100, just to make the numbers easy to deal with. That in the beginning, when the sample was created, when it was formed, it was purely potassium. But over time, the amount of potassium has decreased, and it's going to continue to decrease due to this process of nuclear fission occurring, again, spontaneously. On the flip side, the red curve, this corresponds to the number of daughter atoms, potassium atoms, argon atoms in our case. So in the beginning, the sample in question was purely potassium. There were no argon atoms in that rock sample yet. So that's why we start off at 0 on the bottom of this graph. But as time goes by, the number of argon atoms increases in a very interesting mathematical way until eventually it's going to approach a whole number, 100, just to be simple in this case. But each of these numbers corresponds to one half-life. And again, half-life is the amount of time required for half of the parent atoms to decay into daughter atoms, into daughter nuclei. What's important is that I want you to notice that both of the curves, the red one for the daughter nuclei and the blue one for the parent nuclei, they cross paths, they overlap at a very specific location, one half-life. Here's the reason why. After one half-life, we've lost half of our parent nuclei. Well, if we started off with 100 and we lose half, how many are left over? Well, 50 of them. So that's the location on the graph for the blue curve, which is the number of potassium atoms, parent nuclei. After one half, there's only 50 left. Well, due to conservation of mass, if we had 100 atoms in the beginning and 50 of them have turned into argon, then that means that we've lost 50 potassium, but we've also gained 50 argon in this idealized, oversimplified case. So we've increased 250. That way, the value in red at this location and the value in blue at that same location still add up to 100 total atoms. And that's going to be true for every location. So for example, let's just say that in a rock sample, just hypothetically, that we know that there are 87 atoms of argon and 13 atoms of potassium. It doesn't work this well in actual measurements, but let's just pretend that we know this information through a geological or a chemistry-based analysis. Based upon that knowledge, sometimes called a priori, which is kind of a Latin phrase for know ahead of time. But based upon that knowledge that we know about the rock from some source, some method we don't care about, let's see if we can figure out the age of this particular sample when it was first formed in the past. So what I need to do is I need to find a location on the graph which corresponds to 87 atoms in the argon, aka the red curve location, and 13 atoms of potassium, aka the blue curve location. Well, in the beginning, there's 100 atoms of potassium. That's way too high compared to 13, so I need to keep moving to the right. Okay, here's 50. That's still way too high. All right, here's 25. All right, that's still kind of too high. But if I keep kind of going further and further and further out, the number keeps dropping lower and lower and lower and lower. I just want to get to a location that's about 13. So maybe, for example, right about here. This is the location on the blue curve corresponding to 13 atoms of potassium, and directly above it is a similar location that corresponds to 87 atoms of potassium. Why are they matching up? Why do they have to line up? Well, 87 plus 13 is 100. The total number of atoms at any point in time, at any location on the graph, has to add up to a value of 100, regardless of when we care about. But nonetheless, what we're going to go ahead and say is that these two dots, the blue one for the 13 and the red one for the 87, if I look at them vertically, they line up with this location, 3 half-lives. And if I know that I'm dealing with potassium, I can go to a physics textbook and I can determine, I can just kind of find out, I can look up, I can do a Google search, I guess you could even say, of potassium's half-life, which it turns out is 1.31 billion years. And by multiplying the number that I've gotten from this graph by using these kind of already known ahead of time numbers, then what I can do is I can multiply the number that I've just found from the graph by the half-life of my sample, potassium in this case, and that multiplication, which gives us 3.93, that gives us the age of that sample when that rock was first made, as being 3.93 billion years old. Now, this is just a toy case. This is just a purely hypothetical example case. But the key thing is, as long as I can figure out where these numbers intersect vertically on a graph, where they pass through the x-axis, 1, 2, in my case 3, or whatever number, could even be something in between these numbers if you want to get really complex. But whatever number that is, 3 in this case, multiply that by a constant, a number that's known in physics, and that gives you the age of sample, aka how old your sample is, to have undergone so much nuclear fission to have 13 atoms of potassium left from the 100 that it started with. This is a pretty old sample, to be honest. Okay, so this process that I've shown you here, for our class, you will have to do it. Okay, hold on, don't panic yet. You're going to have to do it, but not necessarily as complicated as this one. So what do I mean by that? Well, if you have to do a calculation like this, I could give you a graph, but probably not. I'll probably just give you the number of half-lives. And I might give you the age of the sample, aka 3.9.3 billion, or I could give you the half-life. But either way, I'll give you 2 of these 3 numbers and ask you to figure out the third one. It's just multiplication to find the total age, or if you divide this number by 3 half-lives, then you can get the half-life of the sample, aka you can figure out what material you're dealing with. But the numbers that we'll have in this class, I'll make sure that they're easy whole numbers. Like 1.31 is a true value, but if this were to be on a test, maybe I would make it 2 or 3. That way, when you multiply 3 times 2, you would get 6 billion years old. Okay, that's an easy to tackle number. So if this is on the exam, and there's no guarantee that questions are chosen at random, but if this type of question is on the test, it's going to be whole numbers only, no decimals. I'm not going to make it nasty like that. So that'll help kind of keep the difficulty down. And as long as you have at least 5 fingers, you can probably do the multiplication on your fingers, like 3 times 2, okay, 2 groups of 3, that's 6, so 3 times 2 is 6. Okay, I'm good to go. So as long as you have at least 5 fingers, you can do the multiplication or the division on your fingers, and therefore you're good to go in that sense. So if this example was a little bit tricky for you, go back through the previous part of the video, see if you can understand of how I got to 3.93 billion years old. And then once you're comfortable with that, then you can go ahead and end the chapter at that point. So thank you everyone for listening. Now that we're finished with chapter 7, a kind of brief overview of certain aspects of the solar system, starting in chapter 8, we're now going to look at a more detailed view of individual objects within our solar system, one at a time or a couple at a time, for the next several chapters.